Our next speaker is Espen Telesken from EM Logic. He's the managing director there. He's going to be speaking about FPGA requirements tracking and traceability matrix. Okay, he's based in Norway. He's author and architect of UVVM, which stands for Universal VHDL Verification Methodology, and that's an open source resource. He has a strong interest in methodology, cultivation, pragmatic efficiency, and quality improvement. And he gives lots of presentations at various international conferences. He's also given courses on FPGA design and verification. For both UVVM and his courses, he tries to make things as easy to understand and use as possible. Okay, and I'm going to hand over to him now.
So just before I start, I just want to briefly say that I'm from a company called EmLogic. We're an independent design center for embedded systems and FPGA based in Norway, just outside Oslo. Started only 4 years ago, had a pretty extreme ramp up from 1 to 43 persons, out of which 18 are on FPGA. And we're a verification IP and methodology provider through UVVM, as Mike mentioned. We also do courses, as was also mentioned, and let's then start with requirements tracking. So what is requirements tracking? This expression is used in many different ways, and it's used everywhere, any business, any domain. I think in our domain, it could be anything like used in a complete large system consisting of multiple subsystems for embedded systems, for FPGAs, and of course going all the way down to FPGA modules as well. Requirements tracking as an expression is very often used for the system requirements hierarchy, as in mapping requirements from one level to the next level down, and then going further down to FPGA or FPGA modules. And of course, also just going from one high level down to FPGA modules directly, but then also via these levels. And also going the other way around, showing how the requirements for an FPGA module, for instance, actually arrived from an embedded systems requirement in the first place. This is one way of looking at requirements tracking, but the expression is also very often used for requirements versus testing and verification. So that means FPGA requirements in our case, and the testing of these requirements. And that, of course, is the focus in this presentation. So what you want to do here is to assure that all requirements in the specification have been verified. This is also sometimes known as requirements coverage or requirement specification coverage even. We just tend to call it specification coverage because then we know what we're talking about and not mixing it up with this system's requirements hierarchy, requirements tracking, for instance. So let's look at how we can define these requirements. So let's take an example with a motor controller and look at some sort of a really reduced requirement list. And it could be, for instance, that the acceleration should be a certain thing. We have requirements to the top speed, requirements to deceleration, and requirements to the final position of this motor. And there could, of course, be lots and lots of other requirements as well to this motor controller. They must be specified somewhere. People use totally different ways of actually defining these requirements. Some use Word, Excel, Jira from Atlassian, or some kind of dedicated requirement tracking program, for instance. And also the formats differ a lot from one tool to another and from one user to another. Could be from something as simple as a non-labeled document format with no sort of specific label for the requirements at all, basically just prosa. Then it could be also an inline label format where you write your specification and then just put your labels inline, to a more sort of strictly labeled format like this one, where you have the requirement label almost as a heading, and then the actual requirements come underneath. The formats could also differ, for instance, from how you handle group requirements. For instance, it could be one requirement applied to a complete table of requirements. So basically you have just one label for that. Or you could have a system where you have one requirement label per single entry in this table, or single combination in this table. And the same applies for protocols. So you could have one single requirement for the complete axis stream, for instance, or you could have multiple requirements, that is, one for every single sort of sub-requirements within this protocol. We have to label the requirements, but again, there are also different formats that would be acceptable. Let's look at how we can define these requirements. So for safety, label requirements are definitely mandatory. But they can be labeled in many different ways. There is no sort of strict rule to that. So you could have something like a rec acceleration max in this case, or you could just use a narrower version, smaller version like rec ac3, as in the acceleration requirement number 3. And have you even seen cases where you just have R or requirement and then just a number? And this differs from company to company. Of course, if you have really pure textual names, then you have full flexibility in the naming and also in how you sort of add requirements during the development. But it's more common with some kind of numbering. And if you have it pure sequential, that is, you increment by 1, then of course you have a problem if you insert a requirement later on. So that's why lots of people actually leave ranges open. So they start basically by incrementing by 10. And that means later on they can add requirement number 17 or 3 or whatever inside the already defined requirements. So you can have a good sort of sequential list of the requirements in your final requirement specification. We also need to define the requirements methods, and that could be lots of different things. So if I think, for instance, in the previous ECSS requirements or the ESA process, there were 4 different methods defined. Now there are 5. So there's analysis, simulation, test, review, and inspection. And this also differs from one sort of requirement traceability philosophy, and also different certifications. And some of these requirements may actually require multiple methods. So it's quite common, for instance, to require that one requirement must be both simulated and tested on real hardware. It could also be that it must be simulated and also reviewed. So there are lots of different ways of specifying the methods as well. And for most safety applications, you would specify the requirement method inside the requirement specification document for that to be reviewed with the actual requirements. Good also that you have split methods. So for instance, that you do a simulation of some details of the requirement, but then you go for a lab test for issues that take too long to simulate. All this has to go, of course, into the requirement specification document in that case. Anyway, in this presentation, I'm only going to talk about simulation using verification and test benches. So I should also mention that there are other coverage metrics because people ask me about that. Of course, you have code coverage, which has basically no relation to this at all, which is just a metric on how much of the code has been verified. And it doesn't really care whether the code is relevant or not. So just skip to the next, which is functional coverage. And people think, well, sort of people tend to sort of mix these two. Yeah, not really knowing which one to use, because there are several similarities. But for specification coverage, most of the requirements cannot be marked as verified or covered just from one or a few values. Basically, what you have to do is to do a complete sequence in your test sequencer. So maybe you write to some registers, you set up some inputs, you check some outputs, and you repeat it even several times, checking responses and added new stimuli. And then after a while, you think, yes, now I have verified this requirement, and then you can tick it off. And also application area and customers, users of these systems often require different reporting views. I'll come back to that. But of course, functional coverage could definitely be used as an input to specification coverage. So one of the requirements could, for instance, be that in order to have verified this requirement, we must have full functional coverage on some of the details here. But functional coverage is not the same as specification coverage. Let's look at how we can trace the requirements. So first of all, of course, we need to specify all the requirements, as I just mentioned. So we have these, in this case, 4 motor requirements. Then we need to track these requirements through verification. And then we have 2 different sort of kinds of traceability. We have forward traceability, and that is, like you see in the table below, for every single requirement, we just have to make sure it has been verified. So we need to basically note down in which test case has this requirement been verified. Then we have backwards traceability. So going the other way around, meaning that for every single test case, which requirement does each test case cover? And this gives us basically what is called the Requirements Traceability Matrix. So we have forward traceability and backwards traceability. Some RTM approaches suggest a pure one-to-one relation. That is, that every requirement is tested in one dedicated test case. And I'm not sure why some people sort of think of that as a good idea. I think maybe that could be because that is what their tool supports. And I don't think that is a good approach. So what you want to have is, of course, an efficient specification coverage. And that a one-to-one relation between the requirement and the test is not efficient. Because let's again go back to this motor example. What if multiple requirements could be covered by the same test case? Well, so we could be turning something into a given position, right? The first thing we have is the acceleration requirement. And with this approach, we need to make a test for that. And then we need to make a new test for the speed requirements, a new test for the deceleration requirements, and then a new test for the final position. But that means we now have 4 different tests for these requirements. Whereas what we could have in this case would be to have one single test case where we first test requirement 1, then requirement 2, then requirement 3, then requirement 4, because they do happen in a given sequence, in given order. And of course, this is an example with 4 requirements. And what if you have multiple many requirements that could in fact be tested in sequence? And even worse, what if most of these requirements are things we can only verify at the end of this sequence? That will be extremely time consuming. It's far more efficient to test multiple requirements per test. Then let's look at these requirement versus test case relations. So for a really simple test case, then it would be quite often sufficient to just have a list of requirements and not sort of specifying in which test case they need to be verified, i.e. you can basically verify them anywhere as long as you verify them. But for a high quality process, like for instance for safety, we have to specify the test case. So that means we have to specify somewhere that motor requirement R1 is to be tested in test case A. Of course, we would use better names, but you know what I mean. But when should we specify in which test case a requirement should be executed? Should that be before, during, or after the test bench development? We could, of course, say that it needs to be before. I know some sort of processes require that, but it might not be that efficient. Some people do it during the test bench development. And of course, if you could do it after the test bench development, then you might even have the answer to where these requirements are actually tested. Or you could do something in between, where you start by making your test benches, and then you find out where it makes sense to test these different requirements, and then you make your plans, requirements, and where they should be tested, and you stick to that. Also, how should we describe our sort of verification? Let's call it a recipe. Should that be a long recipe covering multiple requirements, or should be a one-to-one relation between a brief recipe, sorry, per single requirement? That's also different approaches, and if you go for really high safety, then I think that it's the latter one that you should use. But it's quite common to also use the first one here, which might be easier to use, might be fastest to use, but maybe doesn't give the same kind of quality assurance. And I think that we should allow for flexibility to change the test cases during development, because that is more efficient. The most important thing here is to have the traceability, to be able to track exactly where something is verified. And it's even more important to go for efficiency when you have a good tool that can assure that you do have a good track of your testing and your requirements. Let's go back to the Requirements Traceability Matrix. So a full RTM typically includes the requirements, the test, results, and issues. And in my opinion, I think issues or deviations, whatever we call them, are not really needed in this table because we need to have full compliance anyway. It could be relevant for other requirement methods, but for simulation, as we're doing, I think we should always assure the requirement will give us a pass or fail, and that means, of course, a pass in the end anyway. So a suggested RTM, in my opinion, would be a requirement, a test ID, that is where it's verified, and then the result as pass or fail or compliance. If you look at this table here, you will see that for the motor R4 requirement, I have written the compliance here as it could be compliant, could also be non-compliant. And that is an issue that turns up when you start working with this. And in this case, it could be that, in fact, the motor R4 requirement passed in the test. But as you can see from test case C, motor R3 requirement was also tested in the same test case, and that failed. And then, to be really conservative, you could say that if a test case has failed for one requirement, then it should also fail for any other requirement within that test case. And for the last one here, motor R5 requirement, you can see that, or what I intend to show here is that you might actually not write down the test case where it has been verified or where it should be verified when it hasn't actually been tested, because it could be that it is not known or decided when executed or before executed. Then you have another table where you have test cases versus multiple requirements. So you can see here for test case C that this test case C tests both requirement 3 and requirement 4. And then you have requirements versus multiple test cases. So in this case, you see that motor requirement R2 has been verified in both test case A and test case B. So these are sort of extensions on the requirement traceability matrix that give you more information, really useful information. What if I have compound or group requirements? I just briefly mentioned that previously. And so a requirement may refer to a complete table or protocol. And how should we handle that? So alternative one would be just to say that, well, we need to remember to check everything. And then we just tick it off. Yes, I think we remembered everything. But that's, of course, that's not a good approach. And it's totally not acceptable for safety. Could be to modify the requirement specification document. And just change the names and add a sort of extend the names or modify the names, as you see here. Axis stream, for instance, could be split into ready and valid and so on. But that means it requires modification of an approved document, and that might not be a good approach either. And then it could be to also add this new level in the tool, not in a requirement specification, doing it the same way, but not modifying the requirement specification, but define sub-requirements in the tool and track against these sub-requirements. And only when all are okay, the requirement is okay. That, of course, requires tool support for this. So another questions that might pop up is that what is the requirement?
Hi, Aspen. Sorry to interrupt you. You have 8 minutes to go.
Yep, thank you. So what if a requirement must be tested in one specific test case, but passes somewhere else? What if it may be tested in any of multiple specified test cases? That's a good approach. What if it must be tested in multiple specified test cases, every single one of them? And what if a requirement has changed name compared to the requirement name in a legacy module, for instance? All these are important functionality for requirements tracking. And also have some common process weaknesses. Could of course be that, could be for instance, that the development requirements are ignored, like for instance, design for simulation, design for lab test, not included in requirement list. Also that cross coverage is very often not included, as in 2 different requirements must be tested simultaneously in different variations. This definitely reduces the value of this RTM approach. Often this could be because it's conveniently forgotten because it's more complex, or it could just be a lack of awareness. There are available RTM tools around. The major tool vendors have this functionality available, but they are often very expensive. There are also free tools and methodologies available, but the main problem for these tools is that they have this approach with one single test case per requirement, and that's not efficient. UVM, on the other hand, offers full functionality. So briefly mention, what is UVM? It's a universal VHDL verification methodology, free, open source, structured, and improves verification efficiency and quality in general, recommended by various players in the industry. We work with ESA on various ESA projects to extend the functionality, and it runs on any VHDL 2008 compliant simulator. We focus a lot on quality and efficiency in UVM. This is the complete UVM system. Just going to briefly mention that with something called utility library. We have BFMs, we have verification components, we have constrained random functional coverage, watchdogs and monitors, scoreboards and error injection. We have a large set of BFMs and verification components available. All of these are also open source. And then we have specification coverage. And UVM covers all the functionality given in this presentation. So I'll just briefly show you how it works. So we have to extract requirements first, giving us this requirements list, as you've seen before. Then we implement the test case, and then we run the test case. And you can see from the test case here that first we initialize the test case, making this test coverage file. And then we tick off basically every single requirement that we cover after having done a good sequence of stimuli and checking. And we keep on doing that, and some requirements might of course fail. And if they fail due to an unexpected alert, for instance, they will be failed also in this CSV file, and so on and so on. And then we finalize this at the end, and if there has been an error, then it will actually fail the complete test coverage file. Then at the end, if we have multiple test cases, we run a Python script to collect everything and generate these various report files. In this case, we just assume that everything passed. So we have a minimal specification coverage file here. And we have also a specification coverage showing the test case versus all the requirements it has covered. Then if we have multiple test cases, I just want to briefly mention that, then each test case generates a partial coverage file. So in this case, you have 3 different partial coverage files. You run the Python script. In this case, you have one minimal compliance file. We're just showing you one test case where this has passed and is compliant. And in the other case, you have an extended compliance matrix where you show all the test cases where a requirement has been tested. And then, by the way, if the test case fails, then the test case name will be replaced by a note to check a file called non-compliance. And then, of course, you also have the test case list here. We also have more capabilities. You can define the strictness level. You can accumulate, of course, over multiple test cases. And you can run multiple test cases inside each test sequencer. Specify at least one or multiple test cases must pass, or that requirement must be tested in multiple test cases. And you can also map requirements in one file to requirements in another file. And we also have additional files for important user notifications, like warnings that should be checked, and also compliance that, of course, must be fixed before you complete this. So to summarize, for specification coverage, that doesn't in itself say anything about absolute quality. That depends on the developer really testing the right stuff. It depends on a good requirement specification, and it depends also on compound requirements being split into testable sub-requirements. But given a good test case that do what they intend to do, then specification coverage will check and ensure that all requirements have actually been verified. And it's quite common just to do this as a mental exercise, and that's not good enough at all. It's always better to use a written, repeatable approach. So summary for UVM, it's being used by both FPGA and ASIC designers for mission-critical ESA and NASA projects, for DO254, and for high quality in general. Also developing this in cooperation with ESA, and we're now in a 3rd project with ESA and updating and extending this. There's no lock-in. You can just use this and nothing else inside UVM, and it will result in definitely much better quality, better efficiency, and less boring manual documentation. Okay, thank you.
Yeah, we do have some questions for Espen, but unfortunately we're right against the time. Just for information, we do stay on time because we've got people on the line as well. So I think we should just say thank you to Espen. Thank you.
Thank you.